Welcome. My name is John Dankanich, and I'm the Capability Lead for In-Space Transportation for NASA. And this video is a quick introduction into the GO thrust area for NASA and how it fits in the technology strategic framework. The GO strategic thrust area has the objective to ensure rapid, safe, and efficient transportation. This is split into three disparate outcomes. The first is space nuclear propulsion to enable fast in-space transits, which is heavily focused on the Mars Transportation System application. This is actually both nuclear thermal propulsion and nuclear electric propulsion. The second outcome is to have the capability for cryogenic fluid management, which includes cryogenic storage, transport, and fluid management technologies for surface and in-space applications. The cryogenic fluid management area is not limited to, but is heavily weighted towards human exploration applications, such as the human landing systems, in situ resource utilization liquefaction, cryogenic transfer, and as propellant depots for resupply, but overall on establishing the capabilities within the community to successfully implement cryogenic architectures with predictive performance and acceptable risk. The commodities of most interest are hydrogen, liquid methane, and liquid oxygen, though we do occasionally include helium and supercritical xenon with our investments in fluid management. The third GO outcome is to have developed the advanced propulsion technologies that we need. Advanced propulsion further captures the propulsion-specific technology investments to enable future science and human exploration missions, as well as commercial objectives with both strategic and tactical investments for maintaining U.S. leadership in propulsion capabilities. You can see looking at this chart that the in-space transportation systems capability area really touches a large fraction of the overall NASA technology taxonomy. I could easily have made this chart far more complex and discussed the range of interdependencies. We leverage the strategic framework for an integrated plan with all of our system capability leadership teams and our principal technologists in agreement on priorities, and also for maintaining communication and awareness, which is critical to the community success. We have been working internally and externally to have an inclusive process. This allows us to clearly communicate our expectations with stakeholders, both on the performing organization side and also on the customer user side. The internal review of these disposition packages and the disposition of comments and the responses that we're going to be getting from the requests for information are forcing functions of that communication on both the needs and expectations. Your input and engagement will influence the execution, alignment with, and communication of the strategy, and will also pivot the strategy where greater alignment or a shift in focus is required. Direct ties to the strategic plan include the Nuclear Technology Development Area, and we also work closely with the Space Nuclear Technology Project and the Propulsion Principal Technologist. Under the Cryogenic Fluid Management Technologies, they are tied closely and in fact formally mapped to the thermal domain of the NASA taxonomy and our Thermal Systems Principal Technologist. Many of the nuclear propulsion needs also overlap with the power domain for nuclear fuel, energy conversion, and the power management and distribution systems. For entry, descent, and landing, it's not only a critical interface for handoff between the in-space transportation and the beginning of the entry phase, but there are often the same technologies being used with respect to propulsion. The same systems may be used for in-space maneuvers and for the supersonic retropropulsion, or with deep throttling for landing. Other technologies still are formally in the entry, descent, and landing domain, such as solar sails and booms that are under the entry, descent, and landing domain for drag sails, yet are critical to missions such as Solar Cruiser for providing in-space transportation for the Science Mission Directorate heliophysics missions of interest. Transportation for future Mars architectures is also enabled through orbit servicing and proximity operations, as all of the transportation options requires autonomous fluid transfer and in-space aggregation. Also, it seems that in the end, nearly all of our developments trace to both advanced manufacturing and new material developments for either performance or in some cases cost enabling of the technology. Certainly, there's also need for infrastructure for sustainable vision of human exploration. And finally, the level of autonomy and health monitoring is still to be refined, but autonomous systems are pervasive throughout the GO strategic outcomes. The GO technology development strategies shared with the community vary with respect to the three strategic outcomes. The space nuclear propulsion technologies are dominated by tactical investments to support nuclear options for human Mars transportation solutions. As mentioned a few minutes ago, the cryogenic fluid management technology domain matures architecture-independent cross-cutting capabilities for systems using cryogen commodities of helium, supercritical xenon, liquid oxygen, liquid methane, and liquid hydrogen for propulsion, fuel cells, and life support applications, in addition to enabling future in situ resource utilization, commodity liquefaction, storage, and transfer. Advanced propulsion has both tactical and strategic recommendations to first mature the propulsion technologies needed to meet the demands of science and human exploration mission directorates for increased performance, extreme environments, and reduced cost. And then also advanced propulsion to push the state of the art to maintain U.S. leadership in space propulsion for civil and commercial space applications. Overall, the GO thrust will include a range of investments and procurement approaches across the full spectrum of technology readiness levels. Within the Space Technology Mission Directorate, this includes early stage innovations to mature novel concepts, such as the rotating detonation rocket engine, the Space Technology Research Institute for higher power electric propulsion testing and modeling, supporting nuclear electric propulsion, the Space Technology Graduate Research Opportunities for fundamental research and preparing the future workforce, SBR and STTR investments to lever industry and research institutional capabilities within the community. For example, small set propulsion solutions, sales, IEEE parts, and extreme environment components. And then there's tech maturation activities for our mid-TRL needs, such as advanced manufacturing, nuclear electric propulsion thrusters, extreme environment systems as well. And then we're leveraging public-private partnerships for commercializations, such as that we have with our cryogenic fluid management demonstrations, our tipping points, also sub-kilowatt electric propulsion system development. And yet there's still a range of integrated technology demonstration missions for hydrogen technology demonstrations, nuclear electric propulsion, and nuclear thermal propulsion. The goal is to retire the risks for the future ambitious manifest that we have to execute within NASA. On the last slide, acronyms are provided for reference. Thank you.